tape rolling, and let me give both of you so what we're talking about now is magnetic moment of the electron. And if you just use the Dirac equation, and in fact, if you just do relativistic quantum mechanics in terms of the Dirac equation, you see that what comes out is a factor of 2. And the correction to that comes from a certain vertex diagram that we'll look at today. Meanwhile, let me first prove for you the Bourdon identity, and then we'll go on from there. The Bourdon identity is U bar of Q times Q mu plus P mu. U of P is 2m U bar of Q gamma mu U of P, so it's 2 terms, plus I U bar of Q sigma mu nu Q nu minus P nu U of P. Now here, sigma mu nu is I over 2 gamma mu gamma nu. And let me say that in Weinberg's notation, now of course Weinberg has gamma matrices that differ by I from Schwarz's because he uses a different metric. So I guess if I correct for the metric, this would be I over 4 gamma mu gamma nu. So in Schwarz's language then, I'm taking this from Weinberg chapter 5, where he has a remarkable section on Dirac matrices, by the way. Anyway, one of the remarkable things about the Clifford algebra is that, in fact, this is in my book also, that the commutator of 2 gamma matrices is a generator of the Lorentz group. And these guys satisfy the algebra, the Lie algebra of the Lorentz group. And in particular then, this is the, if you have the IJ part of this, that gives you the spin part. Okay, now, so what we want to do is we want to focus on this term then, because that will be the one that, in other words, this is angular momentum. Okay, the generator there would be Jij really, I over 2, the gamma I, gamma J, and this thing is something like J dot B. In other words, angular momentum dot magnetic field. That's the thing we're looking for, so it's part of the sigma mu nu thing. Okay, let me prove this Bourdon identity. First of all, you recall that the general definition of the gamma matrices is that the anti-commutator, or the symmetric product, basically, is 2 eta mu nu, and consequently the commutated gamma mu gamma nu, which of course is gamma mu gamma nu minus gamma nu gamma mu, well, you can rewrite this as gamma mu gamma nu minus, and then using, oh, I forgot to say that this is 2, well, I did say it, 2 eta mu nu. So you can write gamma mu as 2 eta mu nu minus gamma mu. So I'll write this as 2 eta mu nu minus gamma nu. And so this turns out to be 2 gamma nu minus 2 eta mu nu. So that's what the essence of sigma mu nu is. And so now I sigma mu nu, which is minus a half gamma nu, is then, whoops, sorry. This is then eta mu nu minus gamma nu. And now if you think about it, this thing is anti-symmetric in mu and nu. So we don't have to do any computation. We just have to realize that if we interchange mu and nu, we get an overall minus sign. And so this is gamma mu minus eta mu nu being symmetric. Okay, so then we can, the essence of the Bourdon identity, or of Gordon's identity, is to take the matrix element of sigma mu nu. And so we want to write u bar of q, I sigma mu nu, well, times q nu minus p nu, u of p. And so this is then u bar of q, and now we can write this in two different ways. We can write it like this or like that. And the first time we're going to write it this way because we want the q nu to couple with the gamma nu, and we want that next to the u bar. So this is then gamma mu minus eta mu nu, q nu minus eta mu nu minus gamma nu, p nu, u of p. Okay, so I used this one there and that one here. All right. And now we see this becomes a q slash, and on the other hand, eta mu nu on q nu is just q mu. So this is equal to u bar of q, q slash gamma mu minus q mu. And then over here, we've got minus q mu, hold it, that's p. This thing writes almost like an eraser, doesn't it? It's almost as though I make the strike and the chalk erases itself. Okay, so that's p upper mu minus gamma mu p slash u p. Now, the Dirac equation in momentum space, you remember, is p slash u of p is mu of p, and u bar of q, q slash is u bar of q. So, we can then simplify these things, and what we get is that this is equal to u bar of q times 2m gamma mu minus q mu minus p mu, u of p. Okay, this equal to that is the Bourdon identity. And if you look in Schwartz, what Schwartz does for some reason is he interchanges P and Q, producing a minus sign here. And so you might think that his Bourdon identity is different, but it's actually the same. All right, now let's see if I can get a piece of chalk that's a little bit more helpful. Now, what we're going to be looking at is something we'll call IMU. And this is a diagram in which a photon comes in, P, something or other happens. We have Q1, Q2. This piece of chalk is much better. I don't know what it is about this chalk. Anyway, U bar of Q2. And what is it going to be? Well, we're going to write down all of the Lorentz vectors that we can think of. And so that's F1 gamma mu plus F2 P mu plus F3 Q1 mu plus F4 Q2 mu of Q1. So I'm going down to Q2 and Q1, which is what the indices Schwartz used. Now, of course, P is equal to P, well, P, explicitly it's just P is Q2 minus Q1 by, for momentum conservation. And so in other words, we can set this term equal to 0 because we can always represent any P mu term in terms of Q1 and Q2. So we're going to set F2 equals 0. And it's also true that these F1s, F2, F3, and F4, they don't have any complicated matrix structure. They're just functions of they're Lorentz scalars, and so they can just involve P squared, which is Q2 minus Q1 squared, which is Q1 and Q2 are on the mass shell, so these things are 2m squared minus 2q2 dot q1. And so in effect, the only scalar is really q2 dot q1 because p squared can be re-expressed in terms of it, or equivalently, q2 dot q1 can be re-expressed in terms of p squared. So we're going to be thinking of f1 of the f's as functions of p squared. And of course, functions have to be functions of dimensionless quantities, so it's really, they're functions of p squared over m squared. And p, of course, is the photon momentum, so it's not as though it was p squared was 1. Now, the Bourdon identity tells us that p mu, m mu is 0. And so what we've got here, and by the way, this thing is clearly satisfied for the lowest order diagram to this, because the lowest order diagram is m0 mu, which is minus e u bar q2 gamma mu u of q1. And so if you do p mu and mu0, what you get is minus e u bar of q2, and then this is p slash q1, but this is p is q2 minus q1, so this is q2 slash minus q1 slash u of q1, On the other hand, this gives you m, that gives you m, so this is minus e u bar m minus m u 2, 1 equals 0. Okay, so we verify the ward identity at lowest order. In highest order, it was there was a in chapter 14. It strikes me as a little bit of a pity that he didn't go to prove this little term in general. Instead, what he has is p mu on m mu with a bunch of suffixes equals a difference of 2 without the mu. And that's sort of what we're having here, a difference of 2 without the mu, and you get 0. In any event, let us just take this and go on. So if p mu on that is 0, then what we have is 0 is u2 bar, and now this would be F1, and it would be Q2 slash minus Q1 slash. Well, this we've seen is 0. And then we get F2 P mu, so this would be F2 P squared plus this was so much easier in my office. I'm just wondering what has, right, okay, I'm sorry, this is, right, so this is F3, and it's Q dot, Q1 dot, let me get P. P is Q2 minus Q1, so this is Q2 minus Q1 plus F4, Q2 dot, Q2 minus Q1, and all that U1. This is automatically 0. And we already said that we're going to get rid of the this term because we're going to re-express P. We can re-express P mu in terms of Q1 and Q2. So F2 was already gone. And now if you look at these two guys, for these to be 0, you see that this thing is Q1, Q2 minus Q1 squared, but of course Q1 squared is m squared, and this one is, so that's F3, plus F4, and it's Q2 squared, which is m squared minus Q2, Q1, and then the U1. So if this is going to vanish, this is also m squared. So comparing these two, you see you get F3 minus F4. So effectively, F3 is equal to F4. And so that's what this this is. So once we've got it of this form, we can say, well, it has a gamma mu term, and then it has two terms like this. But that means that what we're dealing with is U bar of Q2, F1 gamma mu, plus, let us say, F3, Q1 mu plus Q2 mu. Now you see we can invoke the Bourdon identity because this thing, let me see here. the Bourdon identity lets us rewrite this as, and now I'm just going to rewrite it as minus IE Q bar of Q2 F1 of P squared over M squared plus I sigma mu nu over 2M P nu F2 of P squared over M squared U of Q1. So what, so let's see, the Bourdon identity tells us that something with gamma mu and something with sigma mu nu is related to that expression there. And so here we have a gamma mu and this, and so that gives us the sigma mu nu term. What I'm a bit puzzled by is what happened here. I think maybe I left out a gamma mu there. Let me just check this. I think I left out a gamma mu. Let me see. I've got the, yeah, there's a gamma mu. I just forgot to write it down. I was saying to myself, boy, that looks strange without a gamma mu. So let me fix this. Okay, so now, now things look a lot better, namely that we expect then that if we have a gamma mu and a Q mu, a Q1 plus Q2 mu, then we can rewrite it as gamma mu and sigma mu nu, P nu term, and P nu being Q2 minus Q1. And then in general there'll be some coefficients, and the coefficients are F1 and F2. I've written them as dimensionless quantities, functions of dimensionless arguments. And these things are called form factors. And so they're quite simple in that they're just functions, but in fact they contain, you know, all of the higher order effects are in these form factors. So they're pretty significant things. The lowest order term, which is just IM0, you see here F1 is 1 and F2 is 0, because, in other words, this guy is just 1. And there's no F2 term at all. Now, the F1 affects the gamma mu, and this is basically related to charge renormalization. This is related to the magnetic moment. And if you have F2 equals 0, that's the same thing as G equals 2, which comes from Dirac's equation. And so this F2 is defined in such a way that G is equal to 2 plus 2 F2 of 0. Why 0? Well, because we're talking about the magnetic moment in the sense of a static magnetic field. So the frequency of the photon is 0. And so we're thinking of this thing as low energy. Now, there are a bunch of diagrams that could conceive that contribute to this thing, but some of them are entirely ignorable. For example, you can have this thing come along, and you can have a photon come along a loop, and it can look like this. But this is a correction to the photon propagator. In fact, we were talking about this last time. Then you can have something like this. So, like that. Or you could have something like this. But this is basically mass renormalization of the electron, which we'll go through in the next chapter. Mass renormalization of the electron, but it doesn't affect this vertex here. And so these are all proportional to the gamma mu term. I have my notes on the board. All right. The one that's important for the magnetic moment looks like this. So we have Q1 going in, Q2 going out, P, and I think it's optional whether you put an arrow on a neutral line, but I find it useful because then I know which way the momentum is going. Anyway, I'm going to put a vertex alpha there, nu here, mu there, call this K, P plus K, K minus Q1. Okay. By the way, I was thinking about this business of shifting. And as Weinberg points out, you really shouldn't shift if the integral is divergent. On the other hand, everybody shifts. Now, why do people shift? Well, you see the K that you have here is itself, it's a variable of integration. And you could call this anything you want. The important thing is you just have to have, at every vertex, you have to have full momentum conservation. So if you call this K plus something else, then this thing is K plus something else, and this one is K plus something else. So you can add something to K all the way around, and it doesn't matter. So in other words, shift freedom is apparently intrinsic to these Feynman diagrams. And so we shouldn't worry about it. Okay. Now, of course, P mu is Q2 mu minus Q1 mu. All right, now what is this diagram? Well, it's I M2 mu nu, and it's going to be minus IE cubed I guess I'm going to go this way, times integral d4 k 2 pi to the 4th. So that's this integration around this loop. And now what we've got is minus I eta nu alpha over k minus q1 squared plus I epsilon. So that's this one. That's that for photon. And then what we've got is this stuff. So we've got this one, which is k slash plus m. This one, which is going to be p plus k slash plus m. And then, that's curious. I've got k slash plus m again here. Maybe I should, oh, that's a different, right, k slash p slash, oh yeah, this thing is a photon propagator. Okay, so here's the way it looks. It's u bar of q2 gamma nu I p slash plus k slash plus m over p plus k squared minus m squared plus I epsilon gamma mu I k slash plus m over k squared minus m squared plus I epsilon gamma alpha u of q1. Okay, so this particular one is there, and this propagator is here, and this propagator is there. All right. Now, of course, this G eta nu alpha just means that this guy becomes an alpha, or equivalently, this one becomes a nu. And in fact, now that I see it, we've got all right, hold on here. This thing, I wrote this as a mu nu. It's actually a mu, and in that case, this should be nu alpha. Schwartz is very sloppy with upper and lower indices. I don't know what he's trying to prove by having things chaotic like that. Anyway, this thing will lower this alpha and make it a lower nu there. And so what we've got then is this is minus e cubed u bar q2 integral d4 k over 2 pi to the 4th gamma nu p slash plus k slash plus m gamma mu k slash plus m gamma nu and u of q1. And then over here, big denominator, and here we have then k minus q1 squared plus I epsilon p plus k squared minus m squared plus I epsilon and k squared minus m squared plus I epsilon. All right, well now we use the second Feynman trick, which is 1 over American Broadcasting Corporation, and this is 2 equals 0 to 1 dx, 0 to 1 dy, 0 to 1 dz, and then a delta of x plus y plus z minus 1, and then we divide by xa plus yb plus zc cubed. And so we want A, say, to be this one, B to be the one in the middle, C to be the other, and actually the way Schwartz did it, he took A to be the last one. So A is k squared minus m squared plus I epsilon. B is this one, p plus k squared minus m squared plus I epsilon. And C is then this one, which is k minus q1 squared minus m squared plus I epsilon. All right, well now, the next few steps are technically complicated just because of the algebra. On the other hand, from the point of view of the physics and the mathematics, you've got something down here that's 1 over k to the 6th, and then up here, the worst you've got is a k squared, so the worst possible thing is logarithmic. But when we look for the piece in here that's proportional to sigma mu nu, which is the part that we're interested in, we'll find that that is actually convergent. So there isn't even any need to renormalize or to do the differentiation and integration. All right, so let's write down what XA, in other words, the denominator, the Feynman denominator, it's then XA plus YP plus ZC, and it turns out that it's K squared plus 2K YP minus ZQ1, and these are Lorentz inner products, and then plus YP squared plus ZQ1 squared minus X plus Y M squared plus I epsilon. Okay, that is actually it, and then we rewrite this as K plus YP minus ZQ1 squared minus delta plus I epsilon. And delta here is minus XYP squared plus 1 minus Z squared M squared. Okay. So remarkably, delta has no K in it at all, and we can simplify some of this if we if we shift K to K minus YP plus ZQ1, and that shift, of course, cancels all of this. So this denominator, which was XA plus YB plus ZC, is then all of this. After a shift, it is just K squared minus delta plus I epsilon, and delta not involving K doesn't get shifted. So the word shaft came to my head. Anyway, what's the numerator? Well, the numerator is this god-awful thing here, and N mu is U bar Q2. This is before shift. So BS before shift.
That's M?
N for numerator. In other words, all of this stuff times the U's. So it's gamma nu P slash plus K slash plus M gamma mu K slash plus M gamma nu U of Q1. And let's see, if you multiply that out, and I'm a little puzzled as to how this might all right, so I must say that this Dirac algebra, I thought it was trivial, but now looking at it, it's not obvious to me how it happened. In any event, somehow you can rewrite this as U bar of Q2 times K slash gamma mu P slash plus K slash gamma mu K slash plus M squared gamma mu minus 2M times 2K mu plus P mu U of Q1. So must say I don't quite see that algebra. In any case, we then shift, and after the shift, this thing changes so that minus 1/2 numerator mu AS after shift is U bar Q2 K slash minus Y P slash plus Z Q1 slash gamma mu P slash plus K slash minus Y P slash plus Z Q1 slash gamma mu K slash minus Y P slash plus Z Q1 slash U of Q1, and then a whole new term, U bar of Q2 M squared gamma mu minus 2M 2K mu minus 2Y P mu plus 2Z Q1 mu plus P mu, close parentheses, U of Q1. Yeah, I'm a little puzzled as to how that worked. Okay, now, of course, what we're going to do is we're going to do the Wick rotation. The denominator, in other words, is k squared minus delta plus I epsilon. This then is k0 squared minus k squared. And when we do that rotation, then everything becomes Euclidean, and the k squared is just a sum of k1 through k4, basically, squared. And once we've made that Wick rotation, then that k integration is such that this denominator just turns out to be, this goes to minus Euclidean k squared minus delta, and the I epsilon is gone. So now we have, this is a 4-vector, a sum of 4 things squared, and so you have this O4 symmetry in k. In other words, this is minus I equals 1 to 4 ki squared minus delta minus delta. And so there's this symmetry in k. Now if you look at the numerator, things that involve single powers of k vanish. And moreover, if you have something that is k mu k nu, well, you can rewrite this as a quarter eta mu nu k squared, and in fact, this eta mu nu is really delta mu nu. Once you're in Euclidean, once everything is Euclidean, this is just basically delta mu nu, because, in other words, if mu is not equal to nu, 0. If mu is equal to nu, then it's like k1 squared. Well, this is 4 copies of k1 squared, so you divide by 4. All right, so that's what that is. You then use Bourdon's identity, and you use the fact that the delta function ensures that x plus y plus z is equal to 1. Well, you use those things and a terrific amount of algebra, and then you find that this numerator is minus a half in mu, and this is then minus a half k squared plus 1 minus x, 1 minus y, p squared plus 1 minus 4z plus z squared m squared u bar q2 gamma mu u of q1. And then a term I m z 1 minus z p nu u bar q2 sigma mu nu u of q1. And then m z minus 2 x minus y p mu u bar q2 u q1. Well, obviously it's the middle line that we're interested in, because it's the sigma mu nu topic. Moreover, there are no k's in these two lines. There is a k squared up here, but this is the gamma mu term, and we're not interested in that. We're interested in the sigma mu nu term. So this term, because of the k squared, is going to give us a logarithmic divergence, because once we do this rotation, you see this thing here is minus k squared minus delta cubed. So this is k to the 6th. So the thing is perfectly convergent except for the k squared term, which gives you a log divergence, but that's the gamma mu part. We don't care about that. I'm still puzzled about how we got from here to here. I think I must have skipped something in Schwartz.
Why is the k squared term, why does that give you a logarithmic divergence?
Because it's k squared, it's d4th k.
Oh, yeah, I get that.
K to the 6th, k squared.
You got it.
Yeah.
You got the sphere.
Okay, let me get you candy. Unless you've had too much candy. Anyway, here. Oh! This term actually vanishes, and the reason is that it's odd if you interchange x and y. On the other hand, delta is even when you interchange x and y. So this term is actually 0. And this term we don't care about. And so we're just going to focus on this.
So odd
So-
terms are 0?
Huh?
Odd terms are 0?
No, it's just that what we've got here is we've got this integral dx, dy, dz, and then we have x minus y, and then we have this delta term. In other words, we have minus k squared minus delta cubed d4th k. So this is the thing we were dealing with. But delta, if we look at it there, is minus delta is xy p squared minus 1 minus z squared m squared. So this is symmetric in xy. It doesn't change when you interchange x and y. This changes by a minus sign. This is an integral over x and y. So there'll be, if you interchange x and y here, you get the same weight. You get a minus sign, no change, so it's 0. The integral's 0. It's like integral minus 1 to 1 dx x equals 0, but it's a two-dimensional version of that. All right, so what we're down to is this term, and this is I m2 mu, And this turns out to be P nu, U bar, Q2, sigma mu nu, U of Q1, and then that's multiplied by 4I E cubed M integral 0 to 1 dx, dy, dz. They all go from 0 to 1, but they all have to add up to 1. And then you have integral d fourth k, 2 pi to the fourth, and we're in Euclidean space here, so you have z 1 minus z over somehow I wrote k squared minus delta, but we had k squared minus delta already. When you go to Euclidean space, it's minus k squared, so I don't know. I think that I'm going to write it this way, or maybe that was before the Schwartz rotation. Anyway, this is what we've got. And now, this integral, apart from the z and the 1 minus z, this thing gives you minus I over 32 pi squared delta. That's that thing that we've had so many times. And so gathering this stuff together, what we've got is, remember this thing is, we're trying to extract the F2 term. So F2 of P squared over M squared is 2M over E 4I E cubed M. Well, I'm just sort of gathering everything together here apart from the spinners. Integral 0 to 1 dx, dy, dz, delta of x plus y plus z minus 1. And now integral d fourth k, 2 pi to the fourth, 1 over minus k squared minus delta cubed. This is after the rotation. And I must say, when you do the rotation, you get an extra I here. So this thing, it may be that this, after the rotation there's an I there. In any event, you then have the factor z 1 minus z. This thing is minus I over 32 pi squared. Delta. And remember that delta is minus xy p squared plus 1 minus z squared m squared. So this thing is equal to alpha over pi, alpha being e squared over 4 pi. Alpha over pi m squared integral 0 to 1 dx, dy, dz, delta x plus y plus z minus 1. And then 1 minus z squared, m squared minus xy p squared, z 1 minus z. All right, so that's when you combine the 32 pi squared and so forth, that's what you get. Now, what we're interested in is the limit in which p squared goes to 0. And we're very lucky about that because otherwise we'd have to worry about the pole. So we just go then to F2 of 0, and then if this is gone, the m squareds cancel, one of the 1 minus z's cancel, and this just becomes alpha over pi integral 0 to 1 dx, 0 to 1 dy, 0 to 1 dz, delta x plus y plus z minus 1. One of these guys canceled, so we have z over 1 minus z. Not a dramatically hard integral. If we integrate x, we see that there's one solution when x is 1 minus y minus z. So that just says substitute for x, but there isn't any x, so that integral is gone. And so then we have just alpha over pi integral 0 to 1 dy. And now dy goes from 0 to 1 minus, I'm sorry, this is dz, dy. And now we have z over 1 minus z. The integral dy from 0 to 1 minus z, there's no y here, just cancel the 1 minus z. This is alpha over pi, integral 0 to 1 dz, z. This is alpha over 2 pi. So this is the famous result that Schwinger did this calculation at an APS meeting in, I think, 1948. Anyway, the actual g is 2 plus 2 f2 of 0. And so what we've got is 2 plus alpha over pi. Numerically, this is 2.00232. The best experimental measurement is 2.002319. And then there are other terms, 304, 3617. Looks like a credit card number. So, of course, one of the strange things about, at least it strikes me as strange often, is that the way people now think of this, by the way, the errors on this are plus or minus 3 times 10 to the minus 13. It turns out that well, this is the best measurement of G, the anomalous magnetic moment. It turns out that we can't measure alpha any better. In fact, we can't even measure alpha as well as we can measure G. So the measurement of G is now used to compute alpha. And in particular, alpha inverse is then 137.03, and it's essentially a 6. It's 5,999,070 plus or minus 9.8 10 to the minus 10. So this is the best value of the inverse of the fine structure constant, and it's based on basically a for loop calculation of the anomalous magnetic moment of the electron. So you get something involving alpha and then whatever, x times alpha to the 4th. Oh no, alpha squared, what am I saying? So wait a minute, that's one, it must be y alpha cubed plus z alpha to the 4th, because this is 1 loop, 2 loop, 3 loop, 4 loop. So that's 4 loop calculations. And, just unbelievable. And when you do that theoretical calculation, compare that with the 4 loop, compare the measure value of the 4 loop formula, you then arrive at this value of alpha. So that's how we define the fine structure constant. Okay, so first, are there any questions? And secondly, let me see if I can somehow get straight that, that one thing that did bother me down there, No, I don't see it. I don't see immediately how to get from there to there. Unless, I mean, you know, you can pull the gamma nu through, but that seems kind of tricky, pulling the gamma nu through all of these terms. And I don't know. Anyway, somehow when so there's some Dirac algebra there that I don't see immediately. Okay, well the next topic is going to be an analysis of the diagrams that we left out, namely this thing. So this is a correction to the electron propagator. And what you can see is that this is going to be divergent. Luckily, as I recall, it's only a log. And the reason is that this thing has effectively electrons and positrons rather than just electrons here. And this thing, of course, is a photon line.
So where would the electrons and positrons?
Excuse me?
So the photon.
Well, it's just that in quantum field theory, when you have something virtual happening, you have electrons and positrons. So you've got this you've got all of this. You've got both there. And so what we're talking about here is basically psi of x, psi bar of y. In Schwartz notation, this is vacuum time order product, psi of x, psi bar of y. And we're thinking of these things as, let us say, Heisenberg field operators, in which case they have all the interactions taking place. Or equivalently, the time dependence is the full time dependence of the theory. And so to lowest order, it's the electron propagator that we know, as say the Feynman propagator. But then to higher order, it's something that we'll calculate. We can then say that this thing is equal to d4 p over 2 pi to the 4th e to the minus I p x minus y, some I g of p slash. And g0 of p slash, or I g0 of p slash, is I over p slash minus m, well, plus I epsilon, I think. And so in other words, if you substitute this for that, you get the ordinary Feynman propagator for this thing. And so we'll compute next time the correction. And let's see, I'm not totally out of Blackboard, so maybe I'll say a word about it. Namely that that diagram, the next order calculation is IG2, and this is, so PK, P minus K, P, and this turns out to be IG0 of P slash, that's this term, I, what one calls sigma 2 of P slash, and then I G0 of P slash. And this I sigma 2 of P slash, if you write this as a Feynman diagram, is it's minus I E squared integral d fourth k 2 pi to the fourth gamma mu I k slash plus m k squared minus m squared plus I epsilon gamma lower mu minus I p minus k squared plus I epsilon. Okay, so that's what sits there between the two. And you can see that this formally actually has a linear divergence. But you can sort of see that once you do the Feynman trick to combine the denominators and then shift, the leading term with k is going to be odd, and so it'll vanish. So it's really a log. And so then the question is, I'm going to see whether I can just do this, the thing I did before, which was to just compute the derivative. That's a finite integral, and then integrate. And on the other hand, I think I should also describe the standard way of doing it, because that may, that's what Schwartz uses in later chapters where he gets really serious about renormalization. I don't know. I don't know whether we should go to the bitter end here in renormalization, because there's a lot of other stuff in the book that we want to cover. Yeah. All right, I think we're done. We can turn this thing off. Any questions? Any further questions?